Hello everybody. We're going to start tonight. We're going to talk about vapor pressure of solutions. Get my pen going here. And vapor pressure of solutions means that when a solution is made, the actual vapor pressure of that solution decreases, and we actually call that vapor pressure lowering. That happens to be one of the colligative properties that we're going to talk about. We're going to talk about vapor pressure lowering, freezing point depression, boiling point elevation, and then a fourth one called osmotic pressure. So we'll just see how far we can get. But vapor pressure of solutions, as mentioned, vapor pressures are lowered when a solution is made. This statement is talking about the presence of a non-volatile solute. What that non-volatile means right there is that that is usually a solid that is dissolved. And when a solid is dissolved in the solution, those particles tend not to themselves vaporize. So in this case, the only component of the solution that would be vaporizing would be the solvent. The solute would then be staying in the solution. When you have a mixture of two substances that both are volatile, then you have a little different situation, and we'll see that later on here. The idea behind this is that the non-volatile solute that is added to the solution decreases the number of solvent particles at the surface of the liquid that then have the ability to escape into the vapor phase. And so we'll see a picture representing that here in this lovely little diagram here. So if you notice in this first container here, we have just a pure solvent, and the pressure is about 3, whatever that unit is. And notice that we've got quite a few number of particles at the surface here that have the ability to vaporize and turn into a gas, which causes the pressure here. Now, if you look at the second container, now we've got these little yellow circles, which is some type of a solid that was dissolved in there. And now look at the number of green molecules that are at the surface compared to this first, where the pure solvent is, because we have fewer particles at the surface of this liquid. Once again, it's just the solvent that's going to vaporize in this scenario. You don't have as many particles that are able to vaporize, and thus notice the vapor pressure is lower in this situation. Another factor that's taking place here is by adding this non-volatile solute, there are intermolecular attractions taking place between the solvent and the solute, which is also kind of holding these particles into solution, and those intermolecular forces aren't happening in this situation because you just have your solvent. But the main idea, I think, is that there are fewer particles at the surface that have the ability to then vaporize. So we can actually predict with a law, Raoult's law, what the vapor pressure of a solution is. And when we run a calculation, this is similar to gas laws, that those calculations are predictions. Then if you actually went to the lab and measured the vapor pressure in the lab, you may notice that that particular experiment follows Raoult's law, does as you predict, or it may not, and then we can talk about what are called deviations from Raoult's law. So we'll see that coming up here in a minute. But here we see that with Raoult's law, the vapor pressure of the solution is directly proportional to the mole fraction of the solvent, and this is what's a little different. I talked to you about when you calculate mole fraction, sometimes you are interested in the mole fraction of the solvent, not necessarily the solute, and that happens to come into play here with Raoult's law. This is the law here. Now the PSOLN, that would be the vapor pressure of the solution, the mixture of the two components. And to find that, you take the mole fraction of the solvent and just multiply it by the vapor pressure of the original solvent. Now this little O here, you could say, represents original, okay, or the pure solvent. That's what that's indicating there, versus over here we don't have that little O. Or sometimes even people say that's the starting point, but I usually think of that as the original. Okay, so it's just really a plugging in situation. You may have to solve for the mole fraction, and then you're given the vapor pressure of the pure solvent, and you multiply those two things and you get the vapor pressure of the solution. Or you could have any of these variables. So you may have the vapor pressure of the solution, the mole fraction, and you have to find the vapor pressure of the pure solvent. Just a variety of things that you could do. Just be able to manipulate that equation, and we'll look at some examples here. And this bullet is just telling what all those components are. Okay. All right, so here is just a graph depicting the idea behind Raoult's law. Now here on the far right, we have the vapor pressure of the pure solvent is 1. So what that means is in this scenario right here, we have just pure solvent. As we go down the line, kind of reading backwards on this graph, what's happening is we've added a solute, so the mole fraction, the solvent, is getting less and less and less as you're adding more and more solute. And notice as you add more and more solute, what's happening to the vapor pressure? The vapor pressure is going down. It is a linear relationship and an indirect relationship. But if you're looking at the mole fraction of the solute, but the lowering of the vapor pressure is directly related to the mole fraction of the vapor pressure of the solvent. Okay, so here's an example where we're going to use Raoult's law. Here's our question: what is the vapor pressure of the solution at 25? Because the vapor pressure can change based on the temperature. We have 158 grams of sucrose. They were nice. They even gave you the molar mass for that without having to give you the formula. It says 643.5 centimeters cubed of water. So there's our volume of water that's measured in. And the density of the water at 25 is given here. So again, we are not assuming a density of 1 in this particular problem. They gave us the density they wanted us to use. And they said that the vapor pressure is 23.76 torr. What that is the vapor pressure of pure water. We are looking for the vapor pressure of the solution with having 158 grams of sucrose dissolved. So I'm just going to kind of follow along what we've got written over here. Here's our Raoult's law. Okay, so we're going to need the mole fraction of the water. We're given the vapor pressure of the pure solvent. And then here is what we're hunting, is our vapor pressure of the solution. So you guys, that's why we studied the mole fraction at the beginning. You guys know how to find the mole fraction of the water. Just be careful. You do want the mole fraction of the water, not the solute. So here they're just walking you through that. We need the moles of the solute for our mole fraction. So that's what that conversion is. And then we need the moles of the water. Well, in order to get the moles of the water, we need the mass of the water. So here's our volume of water used. We're going to use the density of the water here to convert that into grams. And then there is our mass of water in this solution. Then we need to convert that to moles for our mole fraction. So here's our grams of water converted to moles of water. And then plugging that into our mole fraction equation, we have our moles of water in the top, and then the total moles of the solution, which would be the sum of this mole and that mole up there. And then this is our mole fraction of the water, the solvent. And then we just use that in the Raoult's law up here. We plug that in for chi, and then we multiply by the vapor pressure of the pure solvent. In this case, it's torr. So our final answer is in torr, and now this is our vapor pressure of the new solution that we have. And what you should notice is we talked about vapor pressure is going to be lowered, and this is our original vapor pressure of the pure solvent, and now the solution's vapor pressure is a little bit smaller than what it was, not significantly. And the more particles we would add to that solution, the lower that vapor pressure would get. Okay, so here they've just explained that in words, but what I want to make sure you understand is this answer here is the new vapor pressure. The vapor pressure lowering, which sometimes a question may ask you, what is the vapor pressure lowering? Well, then you're going to have to find the difference between the original vapor pressure and the vapor pressure of the new solution, and the difference here is 0.3. So this right here would be called vapor pressure lowering, whereas this here, this answer, the 23.46, is actually the new vapor pressure of the solution. So be careful on the wordings of the problem. What are they really looking for? Okay. All right, so here's another one. It says predict the vapor pressure of the solution. Now in this case, different from the previous example, here we were dealing with sucrose. Now we all know sucrose is a covalent compound. Okay, when we dissolve sucrose in water, it does not dissociate. For every 1 molecule of sucrose we put in the water, we get 1 molecule. Okay, now here we have a sample of a salt, sodium sulfate. We've got to keep that in mind. We've got to look at what is our solute that's being dissolved. When we drop sodium sulfate into the water, that's a soluble salt. It's going to dissolve and dissociate. And for every 1 formula unit of these that we place in the water, we actually get 3 particles. We get 2 sodium ions and 1 sulfate ion. And we have to keep that in mind because these colligative properties that I mentioned are really based on the number of particles present in the solution. We really aren't concerned so much about what those particles are as in regards to how many of them we have. So in this case, we're going to employ the fact that that actually does dissociate into this problem. But we are looking for the vapor pressure of the solution. So again, we're going to use Raoult's law. We're going to need the mole fraction of the water. And then it says here they give us the vapor pressure of pure water, again, at 25 degrees. That's the same as in the previous problem. Again, the vapor pressure would change based on the temperature, so we're corresponding there. All right, so then we just run through our calculation to find the mole fraction of the water. So we take the mass of our water, convert it to moles. We take the mass of our salt, using the molar mass, find the moles of the salt. This is going to summed together. This will be our denominator, and then you have the 9.27, the 9.72 in the numerator. Now, the thing that we have to keep in mind here again is the fact that this dissociated into the 3 particles. So when we found the moles of the sodium sulfate here, that's the moles of this entire thing. Okay, that would be that formula unit. When we are looking at how many particles are actually in solution, then for every one of these formula units, we actually get 3 ions. So we're actually going to take the moles of the sodium sulfate and multiply it by 3, and that's what they're doing here. The 0.246 multiplied by 3 for the number of ions present in solution. So this is actually the number of moles of particles of that solute in that solution. And so that's actually going to go into our denominator. I kind of misspoke earlier. So we're actually taking the 9.72 plus the moles of our solute, the number of particles we've got present there in terms of moles, and that'll be our denominator. So our mole fraction for water is 0.929. And then we just plug that into our Raoult's law using the vapor pressure of water and then the mole fraction of water, and we find out our new vapor pressure is 22.1 torr. Now, if they wanted to know what the vapor pressure lowering was, then we would take our original vapor pressure, which is right here, and subtract the 22.1 torr from that, and that would tell us what we call the vapor pressure lowering. This is just the new vapor pressure. And I know I seem to be emphasizing that, but you know, these questions, y'all, get really tricky sometimes, and you really have to read critically. Okay. All right, so that's an example of vapor pressure lowering. Now we're going to, and that was using a non-volatile solute. How do you know the solute is non-volatile? There's a couple indicators in the problem. First of all, typically if it's a solid, it's going to be a non-volatile solute. The other indicator is if it is not a non-volatile solute, they're actually going to provide 2 vapor pressures for you, and we'll see that in a minute. And that kind of will give you an indication that that other solute, or that solute, is actually volatile. So here's a schematic of a solution where both the solute and the solvent are volatile. See how we've got red and blue spheres here in the liquid phase. I don't know which is the solvent, which is the solute, really doesn't matter for this particular scenario, but notice in the vapor phase we also have both blue and red spheres. So that means that both of the particles are vaporizing at the surface, not just the solvent. So that has an implication on the vapor pressure as well. Essentially what you're doing is still Raoult's law, but we're going to do a modified Raoult's law where we're going to actually find the vapor pressure of each component and essentially add them together is what we're going to do, kind of like Dalton's law, partial pressures. But so we'll see how all that works here. Before we do that, we do need to define some things, and one of those is what we call non-ideal solutions. I think I mentioned that before, that when a solution in the lab obeys or follows the prediction made by Raoult's law, then that would be considered an ideal solution. However, oftentimes in the lab, the solution would maybe have a lower vapor pressure than what Raoult's law predicted, or a higher vapor pressure than what Raoult's law predicted. And so that would be called a deviation from Raoult's law, and that would be considered a non-ideal solution. So there's just two different scenarios. You're either a positive deviation or a negative deviation, and it's really based on the intermolecular attractions that take place. Okay, so this slide is talking about what we call a negative deviation, and that occurs when the intermolecular attractions between the solute and the solvent are stronger than the intermolecular attractions of the pure solvent and the pure solute to each other. Okay, so when the solute and the solvent are placed together, the intermolecular attractions are stronger than when they are separately in their pure form. That would cause a negative deviation from Raoult's law. And what that means is the vapor pressure that would be measured in lab was actually going to be lower than what Raoult's law, that equation, would predict. Okay, and then this talks about the energy that's involved in that. And we know that when you have strong intermolecular attractions, when those substances would dissolve in each other or form the intermolecular forces to hold them together in the solution, there would be a lot of energy released from that. So that's what this means, a large enthalpy of solution, and it would be negative. Okay, then this is looking at maybe a positive deviation from Raoult's law. And that would be when you take the solute and the solvent and you put them together, the interactions between the two are actually weaker than when the solute is by itself and when the solvent is by itself. So there isn't a great attraction for those molecules to each other when they've been mixed together. Okay, and the vapor pressure ends up being higher, and that would maybe be because the particles aren't held together as tightly, so they are able to vaporize more easily, which would then produce a positive deviation and a higher vapor pressure than what Raoult's law predicts. So important. Negative deviation is when the solute and solvent come together, stronger intermolecular forces than when they're separate. The vapor pressure ends up being lower than what is predicted with Raoult's law. That's negative deviation, and then positive deviation is the opposite of that. The vapor pressure is higher. I hope this is making sense. Okay, then here's just a nice little graph depicting that for you. Maybe will help you understand the difference between positive and negative deviation. So we've got this graph A is showing you basically an ideal solution where when we mix A and B together, we get this vapor pressure actually ends up being the vapor pressure that Raoult's law predicts. So this is the prediction, and the vapor pressure actually behaves that way. Letter B here, we have the dotted lines are the predicted situations, and then here this is our vapor pressure of the solution. There's a positive deviation, so that means the vapor pressure of the mixture is actually greater than when what predicted by Raoult's law, as I mentioned before. And then here's our negative deviation. You mix them together and those intermolecular forces are stronger than they were when they were separate from each other. So we get a lower vapor pressure than predicted by Raoult's law. That's that dotted line is their prediction, and this would be the actual measured value in lab. Okay, so I hope that helps a little bit. And then this is another chart basically displaying the same information but looking over here at the intermolecular forces. So let me kind of explain what's going on over here. So we have component A and component B, and these are the forces between A and B, or A pure, B. And then when you mix them together, A and B's forces between each other equal or aren't any stronger or weaker than when they were independent of each other. Okay, and that will yield an ideal solution. And then they give you an example here, benzene and toluene. Okay, then this one is, again, the intermolecular forces between A and then the intermolecular forces between B. If those types of forces are weaker or less than when you put them together, there are stronger forces between A and B, then that yields a negative deviation. That vapor pressure will be lower. The particles will not want to escape the liquid as well. And an example of that is acetone and water, and I think we're going to see an example in a minute. And then this is the other scenario where the intermolecular forces of A and B separate from each other are actually stronger stronger when A and B are placed together, and that will yield a positive deviation. The particles are able to vaporize more readily than they were when they were independent of each other, and that gives us a higher vapor pressure. An example would be ethanol and hexane. So I hope that kind of makes sense. You can look at that chart a little bit more, and I'm sure your book does a great job of explaining that. Okay. All right, so here is an example of a solution where both the solvent and the solute are going to vaporize. All right, so we do not have a non-volatile solute, we have a volatile solute. And how do we know that? One of the indicators is if you read the question here, so the vapor pressures of pure acetone and pure chloroform at 35 are these two vapor pressures. So that's your indicator right here that this is both of the components are going to vaporize. Okay, and they gave that to you because we're going to use what I call a modified form of Raoult's law. And here's the modified form. If we ignored this second part, you'd see Raoult's law right here. And so what we're basically doing is finding the vapor pressure of both of those species, the acetone, which is what the A stands for, and the chloroform, which is what C stands for, and then we're adding them together to find the vapor pressure of the entire solution. Okay, so to do that, we need the mole fraction of both components in this case. So I don't really need to go through all that with you. You know how to do mole fraction. In the end, once you find the mole fraction of both components, we find out that it's actually 50-50 acetone and chloroform. So using this modified Raoult's law, we're going to take the vapor pressure of the acetone, multiply it times its original vapor pressure, which is at 345 torr. Then we're going to add that pressure to whatever is contributed to by the chloroform. 50% of that solution, or half of it mole-wise, is chloroform times chloroform's vapor pressure, which is listed up here. We multiply those two together. That'll give us the vapor pressure that's contributed by the chloroform, and then adding those two together will give us the vapor pressure of the solution with both of those components. And so then they're saying, well, comparing this value with the observed pressure of 260 torr, what that means is this is the predicted vapor pressure of the solution with Raoult's law. This is what it was observed to be in lab. Okay, so the vapor pressure in the lab was lower than the actual prediction with Raoult's law. So this would be considered a negative deviation from Raoult's law. What that means again is when chloroform and acetone are placed together, the intermolecular forces between the two molecules are stronger than in pure acetone and in pure chloroform, and that's why it ends up being a negative deviation. The only way you would know that's a negative deviation or a positive deviation is to have the information of what happened in the lab. Okay, so if you were having to predict whether it's positive or negative, you'd have to know what the actual measured value is and compare it to Raoult's law. They're not going to expect you to be able to predict that without that data. Okay, so I hope that's helpful for you. And again, this is the new vapor pressure predicted. And then if we wanted to talk about whether the vapor pressure was raised or lowered, actually look at here. The predicted vapor pressure lies somewhere between the actual original vapor pressures of the pure substances. Okay, and that's oftentimes what happens. Okay, for that, not with the when they aren't non-volatile. So then we got some pretty pictures here. Here's our picture of acetone, chloroform. They are both polar, but when you put them together, this oxygen tracks pretty strongly to this hydrogen. It's almost like a hydrogen bond. Not quite, but it's strong like that, stronger than just the pure substances. So that's your explanation. Okay, so boiling point elevation and freezing point depression are the next colligative properties that we're going to discuss. Osmotic pressure is a fourth one, but I'm not going to be able to get to that tonight. We have seen boiling point elevation and freezing point depression last year or in first year chem. What a colligative property is basically a property that depends on the number of particles in the solution. So we do have to pay attention to what's being dissolved. Are we dissolving something covalent or are we dissolving something ionic? Because that will differ in how many particles are actually in that solution. Remember, those ionic compounds will dissociate and create more particles, and the covalent compounds don't dissociate. So we'll have to take that into account. All right, boiling point elevation is just explaining to you what that is. Boiling point will go up when you make a solution, adding a non-volatile solute to that. And that's because you're raising the boiling point by adding, you're actually what's happening is when you add that solute, you're increasing the vapor pressure. I'm sorry, you're lowering the vapor pressure. And remember, something boils when the vapor pressure equals the external pressure. So if you have lowered the vapor pressure of the solution by adding that solute, then you're going to have to heat that solution up a lot more to get that vapor pressure to equal the external pressure. And so that's where that boiling point elevation comes in with that. Another factor involved is when you add those solute particles, there are intermolecular attractions that are taking place that aren't present in the pure solvent, and that will cause the particles to be held more tightly in solution, and you'll have to heat them up more to get them to vaporize. But it really is based on getting that vapor pressure equal to the external pressure. And in a solution, that vapor pressure has been lowered, so you're going to have to heat it up a lot more for that vapor pressure to match the external pressure, which is what really increases the boiling point. Okay, so here's our equation for boiling point. Maybe that looks familiar to you. I don't know. We did this. This is where we got our ice cream lab in. If you remember doing that, that's about the only thing most people remember from chem, but that's okay. It's a good thing. So here is that equation. Now this delta T here is the change in boiling point, or we call that the boiling point elevation. That is not the new boiling point. We've got to make a difference between that as well. K sub B is the mole boiling point elevation constant. Say that 20 times fast. That's quite a mouthful. That is a table value. And remember, this is substance specific. And so it's based on the solvent. The solvent, what is doing the dissolving. And then M is your molality. Hence, we looked at molality at the beginning of the chapter. Okay. Oftentimes what we're going to do with this equation here is we might be looking for the molar mass of a solute. We might not know what it is, and so we need to take these measurements, and then we can find the molar mass and we can identify what that substance is that's dissolved in there. The other thing we might be doing is trying to determine what will the new boiling point be if we add a certain amount of a known solute. So there's quite a few different things that we could do with this. Most of the time we are not solving for the mole boiling point elevation constant. That's typically a table value you just look up and place in there. But again, based on what the solvent is. Okay, so we're going to look at, this is basically showing the idea behind what happens with colligative properties. So the red line here, remember this is our phase diagram. The red line would be the pure solvent. In this case, most of the time it's water, but might not always be. With the colligative property, when you make a solution, we just talked about that the boiling point is increased when you make a solution. The other effect that happens is the freezing point decreases. So what you'll notice here is that this blue line here basically extends the range of temperature at which this can be a liquid. And that's what they do with the roads, why they put salt on the roads, etc. Sorry, I'm going to pause here for a second, everybody, if I can figure out how to stop this thing.